Everybody, in this video, I'm going to go through our lesson on special right triangles. And there are two different types of special right triangles. And we're going to start by first talking about 45, 90-degree triangles. 45, 90-degree triangles. So these triangles, the three angles measure 45, 45, and 90 degrees. And really, this kind of comes from the diagonal of a square. I'm actually going to say it's formed from the diagonal of a square, just to be the most specific. From the diagonal of a square. And I actually pre-drew a square because this is my second take on the video. Oh no, I just want the square. And I had some troubles with this part, so preloaded it. We have a square here, and the diagonal goes across opposite vertices. Here is a diagonal. And it's a square, meaning all of the sides are the same length, right? Side, 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 side. And all the angles are 90 degrees. And two of the angles have been bisected. So both of them now measure 45. So this is 45, this is 45. And then these two down here are both 45 as well. So if I look at just one of these triangles, one of the triangles is what we call a 45, 45, 90-degree triangle. So let me draw one of those separately and let's see how I do. I'm going to draw. There, that's not bad. All right, so here's the right angle, and then the side lengths are the same, which actually makes this then an isosceles right triangle because the two side lengths are the same. And then that means the two opposite base angles are the same. And we know that's true because they're both 45. Now, what we don't know is the length of the diagonal. But we could find it. We could find it using the Pythagorean theorem. I mean, this is a right triangle, right? So let's use the Pythagorean theorem, which says that a squared plus b squared is c squared, or in this case, the two legs are both s. So s squared plus s squared should equal the length of the hypotenuse or the diagonal squared. Now, this looks kind of intimidating, but I mean, s squared and s squared, that's the same term. So I can combine that to have 2 of this s squared, and that is equal to the diagonal squared. And if I want to figure out what just the diagonal is in terms of the side lengths, I could take the square root of both sides. So the square root of d squared, that's simply d, the diagonal, is equal to, well, the square root of 2s squared is like the square root of 2 times the square root of s squared, which is nifty because the square root of s squared, that's just s. So the square root of 2 times the side length of the square is equal to the diagonal. Or in other words, this diagonal is equal to the side length times the square root of 2. So this leads us to the 45, 45, 90 theorem. 45, 45, 90-degree triangle theorem. I'm just going to abbreviate here. The full name is in the OMHS. But the 45, 45, 90-degree triangle theorem says that the length of the hypotenuse is the square root of 2 times the length of a leg. So one way you may see this drawn is we have x and x as the two legs. So then this hypotenuse is x times the square root of 2. And again, this is a 45, 45, 90-degree triangle, also an isosceles right triangle. 45, 45, 90-degree triangle could be shown to you like this. And then you would have to understand the two side lengths are congruent, meaning these two angles opposite are congruent, and they'd both have to be 45. All right, let's now talk about 30, 60, 90 triangles. So 30, 60, 90-degree triangles are formed from the altitude, or the height, of an equilateral triangle. Oops. I drew an equilateral triangle. I'm going to bring it up here. Equilateral triangle means all of the sides are the same measure. So in this equilateral triangle, we have each side. And the altitude is the perpendicular height from the vertex to the opposite side. Let me kind of shimmy that over. Let's see. And since it is equilateral, that means then, and this is perpendicular altitude, this distance, just 1/2 of the side, is 1/2 of s. So this height, this altitude, divides the opposite side in half. So we really have a 30, 60, 90 triangle because we have the 90 degrees. Each angle of the overall triangle is 60 degrees. And then that angle at the top is split in half. So this is 30, and this angle here is 30. So if I look at just one of these triangles, I'm going to look at the right-hand side. My 90-degree angle, here's my 60-degree, and then my 30-degree. We have the side length, which is really the hypotenuse here, and this shortest leg is 1/2 times the side, or the side divided by 2. Note also that this is what we call a scalene triangle. So this is a scalene right triangle. All right, now I know kind of how the hypotenuse and the shortest leg are related to one another. What I do not know is how this height factors in. So I'm going to kind of set up an equation and try to solve for h using the Pythagorean theorem. So the Pythagorean theorem tells me to square the two legs. So I have s over 2 squared plus that h squared, the longer leg squared, and that is equal to s squared. Now, s over 2 squared is really like s squared over 2 squared plus h squared is equal to s squared. Now, s squared over 2 squared is a lot like s squared over 4 because 2 squared is 4. So I have s squared over 4 plus h squared is equal to s squared. Now, again, my goal is to kind of find this h. So I'm going to move this entire piece of s squared over 4 over. So I'm going to subtract s squared over 4 from both sides, which feels really weird, but I'm just subtracting it to move it. So I now have h squared is equal to s squared minus s squared over 4. And if I want to subtract these two, I'm going to need common denominators, which I could find. I could actually find common denominators for this. I could rewrite these to both be over 4. So let's think about s squared kind of off to the side. That's like s squared over 1. So if I multiply it by 4 over 4, well, s squared times 4 is 4s squared over 1 times 4 gives me 4. So I now know that h squared is equal to s squared, we just said, is 4s squared over 4. And we are subtracting from that s squared minus 4. So I know I did it right because I see the same denominator. Now I'm just subtracting the numerators. So h squared is really equal to 4s squared minus s squared all over 4. So I'm just subtracting, and 4s squared minus 1s squared is 3s squared overall. So I'm going to rewrite this. H squared is equal to 3s squared divided by 4. And if my goal, again, is to find h, I need to take the square root. So if I take the square root of both sides, this tells me then that h itself is equal to, well, the square root of 3s squared over 4 is really like the square root of 3s squared over the square root of 4. And I know what the square root of 4 is. Square root of 4 is 2. So h then is equal to whatever this numerator is over 2. And the square root of 3s squared I can break up into the square root of 3 times the square root of s squared. Multiplication means I can split it up like that. And the square root of s squared we know is s. So h is the square root of 3 times s divided by 2, which is so nice because this is really like the square root of 3 times s over 2. And s over 2, we already talked about that. S over 2 is our shortest leg. So I know then that h, the altitude or the longest leg, is equal to the square root of 3 times the shorter leg. And that leads us to the 30, 60, 90 degree triangle theorem. So 30, 60, 90 degree triangle theorem says that the hypotenuse of a 30, 60, 90 degree triangle is 2 times the short leg and the longer leg is square root of 3 times the short leg. So if I draw a picture of this, here's my 30, 60, 90. This is the 60 degree. This is the 30 that's farther away from the 90 degree. And we know that the hypotenuse is 2 times the short leg. So if our short leg is x, the hypotenuse is 2 times x. And the longer leg is the square root of 3 times the short leg, or x times the square root of 3. All right, let's look at some examples. Oh, just kidding. I have a quick note that I wanted to have us write first, and this is so important. When we're working with radicals and we're working with these special right triangles, you might encounter radicals in the denominator. We do not want that in our final answer. No radicals in the denominator. So if you see, for example, 1 over the square root of 2, that is not a rational number because the square root of 2 is not an integer. It's not an integer divided by an integer. So let's rationalize it. And I'm actually just going to multiply this fraction by 1, except instead of 1, I'm going to have it be the square root of 2 over the square root of 2. The issue here is that the square root of 2 is in the denominator. So I'm going to multiply by square root of 2 over the square root of 2, because that's really just like multiplying by 1. And when we do this, looking at the numerator, 1 times the square root of 2 is just the square root of 2. And then in the denominator, the square root of 2 times the square root of 2 is like the square root of 2 times 2, or the square root of 4, which is so great because the square root of 4 is 2. This is really like the square root of 2 squared. That was the whole reason why I chose the square root of 2, so that it would really just cancel out the squares, leaving us with just 2 in the denominator. So here, rationalized 1 over square root of 2 is the square root of 2 over 2. So this is what we call our rationalized answer. That is very important as we go forward in our examples. So first example, number 1, find the length of the hypotenuse in simplest radical form. Then we are going to draw the picture. So the picture here is of a 45, 45, 90 degree triangle. So I'm going to draw that 45, 45, 90 triangle. Let's try again. It's not great, but it's not to scale. Okay, so this is 45, this is 90, and this is 45. And the diagram tells us that the length of that side is 9, and the side we're trying to find is x. So length of the hypotenuse. Well, in a 45, 45, 90 degree triangle, we actually just wrote this down in our notes. The hypotenuse is the square root of 2 times the leg. So x is really the square root of 2 times our leg, which is 9. And we actually know both of these sides are 9, so it doesn't matter. And I mean, 9 times the square root of 2 is just 9 square root of 2. So that is the length of our hypotenuse in simplest radical form. Number 2, we are going to find the length of side x in simplest radical form. And the triangle looks like so. This angle is 90, this angle is 60, and then we know that this is side x, and this short leg here is the square root of 6. So if this is all I know, I do know that this is a 30, 60, 90 triangle because I know this angle is 90 degrees up top. The bottom angle is 60 degrees. Together, those make 150 degrees, which is 30 degrees away from 180. So this is a 30, 60, 90 triangle. And in a 30, 60, 90 triangle, if I use that 30, 60, 90 theorem, which we wrote up here, the hypotenuse is 2 times the short leg. We actually don't really care about the hypotenuse. We're asked about the longer leg. So let's see. The longer leg is square root of 3 times the short leg. So I am going to take our short leg and I'm going to multiply it times the square root of 3. So x is equal to our short leg times the square root of 3. And our short leg is the square root of 6. So this is really the square root of 6 times the square root of 3. And if I'm multiplying these two together, this is really just like the square root of 6 times 3, which is the square root of 18. Now we are asked to write this in simplest radical form, and I'm betting this can simplify. I know that 18 is 3 times 6, so I could factor tree this, or I could think about the fact that 18 is also 2 times 9 or 9 times 2. So I'm going to say here then that x is equal to 18, or sorry, square root of 18, which is really like the square root of 9 times 2. So now I can split it up across the multiplication. This is now the square root of 9 times the square root of 2. And the square root of 9, I can simplify to get me 3. So x is 3 times the square root of 2. If we were asked to find the hypotenuse, just as a side note, I would simply take this this shortest leg and I would multiply it by 2. So this tells me then that our hypotenuse is 2 times the square root of 6. And I don't think we can simplify the square root of 6, right? It'll just factor through to 2 times 3. All right, last problem that we're going to do together. In the equilateral triangle, find the length of x in simplest radical form with a rationalized denominator. I did not include that on the previous 2 problems because it did not apply. I could have written it if I wanted to. It always applies. You want to have a rationalized denominator, meaning no radicals in the bottom of a fraction. And let's draw this image. That would be kind of helpful too. So it's an equilateral triangle. Pretend it's equilateral, okay? So these sides are all congruent. It kind of looks equilateral, but it kind of also doesn't. So we have this altitude, which is the square root of 11, and we would like to find this side length x, which this is the same on all 3 sides. Now, remember that the altitude is 90 degrees, so that would be included in our image. And because this is equilateral, I know then that all of the angles are the same. So all of these angles are 60 degrees. So I'm just going to write that this is 60 degrees here, which means then that this top angle has to be 30. So this is a 30, 60, 90 degree triangle, and there's no direct relationship between the longest leg and the hypotenuse. I know that the hypotenuse is 2 times the shorter leg, and the longer leg is the square root of 3 times the shorter leg. So I think what I'm going to do first is I'm going to figure out what's the length of this shorter leg, and I'm going to call that side y. So to do this, I'm going to take the square root of 11, and I'm going to undo the fact that the longer leg, the square root 11 is, I'm gonna write that over here, the square root 11 is the square root of 3 times whatever this shorter leg is. So I'm really going to have to divide by the square root of 3. If I want to figure out what this value of y is, I'm going to take that longer side of square root of 11 and divide it by the square root of 3. Because I know the longer side is the square root of 3 times the length of the shorter side. And now this is kind of where that rationalization needs to come in, because I don't want that radical in the denominator. So to get rid of the radical in the denominator, I'm going to multiply by 1, which is really going to be the square root of 3 over the square root of 3, because the square root of 3 is what's in the denominator that we do not want. And if I actually multiply across the numerator, I have the square root of 11 times the square root of 3, which is the square root of 11 times 3, all over the square root of 3 times 3, or 3 squared, which is then just 3, right? The square root of 3 times 3 is really like the square root of 9. So that is just 3. Now looking at the numerator, the square root of 11 times 3 is like the square root of 33. And I unfortunately cannot simplify that further. So I'm just going to leave it as the square root of 33 over 3. Now, that is this side y. So I'm going to say y is equal to the square root of 33 over 3. To figure out what x is, the hypotenuse is always double the shorter leg. So x is double this length of the square root of 33 over 3. So I can simply put 2 in the numerator with the square root of 33, and I will say that the hypotenuse equals 2 times the square root of 33 divided by 3. And this is in simplest radical form with a rationalized denominator. Please let me know what questions you have on this. I encourage you to write down all of your work when you're practicing. You're going to make mistakes. That's part of the process. So do not beat yourself up if you make a mistake, and let me know where you get stuck. I'm here to help.